Welcome to everybody, students, faculty, guests. It's great to be here and to share the work that I'm doing on Mars with you all today. So kind of the talk for today is exploring Mars atmosphere weather. Okay, so I'm a meteorologist in the meteorology department here, but I kind of branched to Martian meteorology as well as Earth meteorology. So one of the themes that we'll kind of see is what are some of the similarities and differences between meteorology on Earth and Mars? And hopefully what also comes out of the talk is a little, why would we be interested in the weather on Mars? What impact does that have on our spacecraft exploration of the planet? What are some of the compelling science questions that we're trying to answer about weather? And what are the tools that we use to explore that? So I'll be using both kind of the spacecraft missions from NASA and others that have sent to the red planet, as well as computer simulations, and the idea of data assimilation, which is bringing those two data sets together to really understand what's going on with the weather on the Mars atmosphere. So I'd like to, first of all, thank a lot of people. I have collaborators at Penn State, University of Maryland, NASA, a lot of other places that have been part of this work, as well as many students that I've been fortunate to mentor here at Penn State who have been part of this project, and without their help, some of these results would not be possible. So we'll begin kind of with the outline here. Right, we'll start out with some of the basics, just to get everyone situated what Martian weather and climate look like. Then I'll kind of explain this idea of what a Martian reanalysis is. This is the product that my group has been creating over the last decade or so to study the weather. And then from there, we want to explore certain aspects of the weather, transient eddies or traveling weather systems, right? Dust storms, which are the big challenge for Martian meteorology, which have big implication for spacecraft operations on the planet. And then we'll look at some other topics should time permit. Okay. So starting out here with some of the basics, this is kind of just a comparison of Earth and Mars. This is about the real size comparison between the two planets. So Earth is about twice the diameter of Mars. So Mars being a smaller planet, you would have less gravity on Mars. So you'd be able to hop if you were an astronaut there. If you had a solar day on Mars, it's 39 minutes longer than the Earth. So those working on the missions, as Chris pointed out earlier in his talk, right? So they start out working on a Martian day that gets 40 minutes later each day. So you get a little bit extra sleep, but not so much fun when you have to work in the middle of the night. Thankfully, I don't think all operations are that way, just at the beginning of some of the missions. And the Martian year is about twice as long as the Earth's. Okay? And the obliquity or the axial tilt of the planet is similar to Earth's, at least right now. Okay, so why that's important, that determines that Mars will have seasons. Okay, at different times in Mars's past, that axial tilt may have been more extreme or less extreme. That's going to change around the climatology for Mars, but I think that's remarkably similar between the two. Okay, primary atmosphere constituent, Earth, 78% nitrogen. Mars is mostly CO2 atmosphere, but much less of an atmosphere than the Earth. So 6 millibars or 600 pascals, right? Imagine how thin the air is at the top of Mount Everest. That's about 300 millibars. Mars is about 6 millibars, right? So much thinner atmosphere even than above the top of Mount Everest. So you have to keep that in mind when thinking about the impacts of dust storms, what will be similar or different to that. Surface temperatures, you can imagine Mars being fourth from the sun will be a bit further away, a bit colder, but we'll see how just extreme or how similar or different those temperatures will be in a little bit. Okay. So speaking about Mars seasons, there's not a strict Mars calendar, so to speak. So we instead use solar longitude. This is a seasonal index that kind of tells us what season we're in. So starting out here with the spring equinox, we then move around kind of to the summer solstice, autumn equinox, winter solstice, and back, 0 to 360 degrees. So that's kind of our best use of a Martian calendar to kind of see where we are with respect to things. Another thing to keep in mind is that Mars is closest to the sun at its perihelion, which is in northern hemisphere winter. Okay, so that's going to lead to some differences between northern hemisphere and southern hemisphere seasons. Another thing to keep in mind with the planet is that because it's so much closer to the sun in the northern winter than the summer, there's actually 44% more solar radiation at the perihelion. So that's again going to lead to this kind of difference in northern and southern hemisphere seasonality on Mars. So how did we learn about Mars? So I'm going to go into a little bit of a history lesson here with NASA's armada of spacecraft that they've sent to Mars over the past few decades. And so this is Earth time from 1960 through to the present in blue. And in red, this is Mars years. You'll see that a lot kind of for how Martians keep time. Okay, they kind of picked the time for Mars year 1 before all the spacecraft arrived at Mars. Okay, so starting out here, this is the Mariner program. The first spacecraft to fly by Mars was in the mid-1960s or so. Up in my office, I have some sample images where we first got a sense of that, of what that looked like close up, right? Kind of going from that idea of Mars with canals as envisioned by kind of the early astronomers in the late 1800s and early 1900s to seeing kind of a more kind of dead world, at least how we thought at the time, with kind of more craters, looking a little more moon-like in our first appearances. Okay, then we have our later Mariner probe. It arrives around Mars to take an orbit, the first orbit of Mars in the early 70s, designed to take pictures of the surface. But when it gets there, it can't see the surface. Why is that? Because we have a global dust storm raging. So thankfully, that spacecraft was in orbit long enough for that storm to abate. We're able to see down to the surface, start to map the planet, get a much better sense of the varied topography of the planet, as well as get some sense of the weather at that time. Okay. We then send our first lander to Mars with the Viking landers in the late 1970s, early 1980s. Right? These actually had weather stations on board. We're actually able to measure surface pressure, like you have with the barometer for the Earth. And we see the patches of weather systems. And it's one thing we learned from the Viking missions is some of this weather was a little more repeatable than the Earth. Let's say every 3, 4, 5 days, we have a weather system move through, but not perfectly repeatable. Still enough to be interesting for meteorologists like myself, who's interested in things that when they're not so predictable. Right? Going from the Viking lander now along to kind of Mars Pathfinder, and then finally the orbiting spacecraft, which I have mostly here on the top. The Mars Global Surveyor arrived in 1996 or so, and that had a geology instrument that looks in the infrared. But what's great about the infrared is not only can we learn things about the surface, but also about temperature structure. So this is the beginning of this data set from orbiting spacecraft that we're able to use to understand the weather at a global scale, not just at one location on Mars. Okay? So starting in around late 1990s through to the present is about the extent of Mars weather that I mostly focus on for my studies. So Mars Global Surveyor had this test instrument, which I'll show you more about. It was followed up by Mars Reconnaissance Orbiter with the Mars Climate Sounder instrument on board. That is also, this one was specifically designed to look at weather, temperature structure in the atmosphere, dust, and water ice. There's actually water on Mars. It's just a matter is there liquid in the present Mars? And if so, how much and where? Okay, but definitely water vapor and water ice. Okay. So we have some other missions here. These are focused on kind of the NASA upper atmosphere. MAVEN's trying to address some of those questions deeper back in time. Did Mars once have a much thicker atmosphere? How quickly is Mars losing that atmosphere over time? And what's interesting about the connection with MAVEN is we've learned that things like dust storms actually change the rate at which we lose atmosphere. So we need to know a little more about storms on Mars to interpret these changes in deep time. Okay? And along while we have these orbiting spacecraft, we also, of course, have the landers. Okay? The Mars Exploration Rover. These were sent in the early 2000s. Here you can see what Spirit and Opportunity look like, about maybe this size. Okay? These were solar-powered rovers. They were designed to last 90 days on Mars. Dust slowly accumulates onto the panel, making it less efficient to take in solar energy. But then dust devils come by and blow the dust off. And these missions that were designed to last 90 days, well, Opportunity rover lasted all the way from the early 2000s to 2018, thanks to Martian weather clearing the dust panel. Right? Now, whereas weather can sometimes be helpful, sometimes weather can end missions. We'll come back to that in a little bit. Okay, looking further along, we have the Mars Phoenix lander. This is one of the few to land near the Martian Arctic. This studied kind of the environment near the polar ice cap until itself was enveloped by CO2 dry ice. Okay. Further along, we have the Curiosity rover. This is a picture from the clean room out at JPL. I got to go out and tour when I was a grad student and see the launch. This is Curiosity's kind of selfie on Mars of what it looks like. Been roving Mars for about the last decade or so, making a lot of discoveries, mostly focused on kind of the geology and astrobiology, but there are some weather instruments on board that we can use to understand weather. Okay, and more recently, we have the InSight lander right here. That was to look at seismology and Mars quakes, but also had high resolution and time barometer for weather. And then finally, the Perseverance rover, the Mars 2020 mission, most recent NASA mission, similar in size to Curiosity. One of the goals, in addition to kind of enhanced tools from what Curiosity has is to cache geological samples so that hopefully a sample return mission can take them back to Earth in sometime in the next decade or two. Okay? So that kind of gives the broad view of Mars exploration. I put more kind of the weather side of this on here, even though some of these primary missions are more on the geology, astrobiology side, but hopefully can make the case that, yes, we do actually have quite a bit of data about Mars weather that we can build on. Okay? So what does the Martian surface look like? Okay, so we now have the Mars laser altimeter that's mapped things pretty accurately. This is a view from Google Mars. You can actually pan around and look at the planet just like you would for Google Earth. And you can see the northern plains of Mars are much lower. This is altitude and flatter than other regions of Mars. If Mars ever had an ancient ocean, this could be a region that might have had that ocean. Okay? That's up for a debate. And then other parts on Mars that we notice, very tall mountains, Olympus Mons. This is 3 times the height of Mount Everest. Okay? So extreme topography, that's going to matter as it comes to weather. Valles Marineris, right? The width of the continental United States, deep as the Grand Canyon or deeper. Okay? So this topography is going to play a role, and we see not only just these individual features, but that the southern hemisphere is a much newer, rather more heavily cratered surface and much higher in altitude surface than the northern hemisphere. Okay? So here you're going to have differences in weather, not just because of the perihelion and aphelion when they occur, when it's closer or further from the sun, but also because of the topography differences between the 2 hemispheres. So what does Mars weather look like? Okay, so if you're a Martian meteorologist, what would you want to try to understand and forecast? Okay, so the one thing I'm going to show a lot of later are these traveling weather systems. Basically, how many of you have ever looked at, let's say, a Weather Channel map or any other company with cold fronts, lows and highs on it? Okay, see a lot of nodding heads, right? So we're going to see what those look like for Mars. Those are the traveling weather systems that move across Mars. That's part of what we study. Okay? Thermal tides. This is something a little more unique. It's not oceanic tides necessarily from gravitation, but this is tides due to the intense solar heating of the ground and in the atmosphere above it. That's going to have a big day-night temperature contrast, which we'll see. We see water ice clouds. Okay? So right here, if you can make out these very thin features right here, that's like a cirrus cloud on Earth, the thin icy clouds you might have seen maybe even earlier today. I think I saw some. Okay? Those are going to be present on Mars. Okay? You can see them located nearby some of the topography, the volcanoes of Mars. So some of them are orographic or forced by terrain. And those are omnipresent on Mars, especially in certain seasons in the equatorial regions and above the polar ice cap. So we do have water. We have a few precipitable microns. So that's much less than the Earth, right? Earth, we think about maybe precipitable water that could be an inch or 2, meaning if you took all the column of water above your head, all that water vapor, you forced it to condense and rain out, how deep would that column be? Okay, so a little bit of water, but not a lot in Mars in the atmosphere. Okay. Is there precip? So there actually was snowfall detected by the Phoenix lander using its LiDAR system. Okay, so some of these seasonal polar ice caps, this is dry ice snow. Some of it is directly sublimating or depositing rather onto the surface. Others might be snow particles actually falling down to the ground. Okay. Surface frosts and fogs. These can be either CO2 or water ice. Okay. We have these polar caps. Okay. This actually changes throughout the year. We have permanent caps that are smaller right around the pole, maybe the 10 degrees of longitude closest to the pole. Okay. And then we have these seasonal caps. The seasonal caps are mostly CO2 ice. They are going to move with the seasons. And we get one in each hemisphere, depending on which is kind of focused around the winter season. The next one is dust devils. How many of you have seen the movie The Martian? All right, so toward the end, there's actually a pretty neat depiction of a dust devil on Mars. I thought that was a more realistic part of the weather. Okay? Earlier in The Martian, you may have something with a dust storm without giving too much away. Right? Keeping in mind, the skies on Mars can darken in dust storms, but if the atmosphere is so much thinner than the Earth, the force exerted by the wind is going to be much less than what damage might have been caused during The Martian. Okay? So we do get bad dust storms, but they may not be able to have the structural damage that was caused there. Okay? So these are going to be the big mysteries that we want to explore. Okay? So if we're trying to look at scale analysis, right, just like we might see for Earth that some phenomena are short-lived. That means on this x-axis, this is time. as well as small in scale. This is the y-axis. Right, so some of our short-lived phenomena are going to be turbulent phenomena, dust devils, things like that. As we go to larger features, maybe the time period of the day, topographic flow, thermal tides. Our traveling weather systems are going to be a little bit larger in size, maybe thousands of kilometers in extent, lasting a few days. We get these regional dust storms on Mars that might last days to weeks and cover continent sizes. And then finally working our way up to these global dust storms that might happen every few years and cover the entire planet. Okay, so just like for Earth weather, we have a range of different scales, a range of weather phenomena. Okay, so for Earth meteorology, we think about the kind of micro scale meteorology, mesoscale, synoptic scale, and then global scale. So I'm mostly a Mars synoptic scale meteorologist, kind of in this range, but we want to be aware that if you're thinking about weather at the landing sites, you also need to think about the topography and some of the local meteorology, as well as what's happening at the large scales that I'm looking at. Okay, so let's see what happens during a dust storm. All right, so I alluded to kind of that first mapping mission. Now, this is a dust storm that was observed by Mars Global Surveyor in 2001. This is a view of the planet from space during normal conditions. We can see craters, we can see clouds, lots of other features. This is Mars during a dust storm. Right, so you see most of the features of the planet have disappeared under that veil of dust. Right, and this veil of dust lasts for months and obscures missions being able to see all the way to the ground, at least in the visible. Okay, so we really need to understand this because there is no analog for these on Earth. Right, we get local dust storms on Earth. We might even get local to regional scale, right? But we don't have anything that covers the Earth in dust, at least in the Earth's present climate, that would be analogous to that. Right, these storms happen every few years. So we know there's variability. It's not regular variability. So we want to understand why. Right? Is it that dust is getting blown around on the planet and getting redistributed? Is it that there's just chaotic variability? Is there any external forcing? Why is this happening every few years? And those are some of the grand challenges for Mars weather that we want to be able to solve. Okay, so taking a look at what it might be like for the Opportunity rover. Okay, here's Opportunity. Here's the kind of a simulation of what the skies would be doing over Opportunity during a dust storm. You can see them darkening. I know when the Martian things got pretty dark, there's actually a tau of 10. So that's how many times you're kind of reducing the amount of sunlight going down the atmosphere. So definitely at least thunderstorm dark, maybe not quite night dark on Mars if you were trying to imagine what it would be like to be in one of these storms. All right, but that's going to matter significantly if you have a solar powered rover. Right? That power production is going to dip significantly. And unfortunately, Opportunity met its demise during this dust storm. And it didn't have enough power. They tried to wake it up after the storm passed and were unable to do so. Okay, so if you can imagine both present missions and potential future missions, right, especially any of those that are dependent on solar power, will care about forecasts of dust storms because that can significantly impact operations. Right, other missions like Curiosity and Perseverance, they use nuclear power. So they're not going to be so impacted by the storms, at least from a power point of view. So how are we going to study these storms that impact missions? Okay, so I want to take you through is how we construct a Mars atmosphere reanalysis. Okay, so there's a few pieces to this. We have spacecraft observations of the planet. Okay, we have a Mars global climate model that's going to simulate the atmosphere. It's going to simulate dust. It's going to simulate clouds. It's kind of analogous to our numerical weather prediction models that we use to forecast the Earth, except here applied to the Martian atmosphere. And we're also going to use data assimilation techniques. Those are how we combine observations with models generally. Specifically, we're going to apply this to Mars. And then finally, we'll want to see, well, we can create this reanalysis product, but how do we know it's any good? Right? We need to be able to evaluate that product against other observations to see how well it's doing at representing the weather on Mars at particular dates and times. Okay? So let's go through each of these steps one at a time. We'll start with the observations. Okay? So we mentioned a lot of attentions on the surface operations, and that's where a lot of the exciting things are being done kind of for the astrobiology and geology. But for weather, right, we want to get data points around the globe. So I'm mostly focused on the orbiting missions and then using the individual stations as kind of verification of that. Okay, so these orbiting missions have usually a polar orbit, meaning every 2 a.m. and 2 p.m., for example, we get coverage of the Martian weather. Okay? That's reasonably good. I know that's not a lot compared to Mars, but we've actually done quite a bit in reconstructing Earth weather using only surface pressure historically. So this is actually reasonable to get a zoomed out synoptic scale view of the Martian weather. Okay, so our first mission, 1997 to 2006, temperature retrievals at about 20 different levels in the atmosphere, but really is about 4 independent pieces of information in the vertical. Okay, so we can see what's going on in the lower atmosphere and then middle atmosphere up to about 40 kilometers. Here we have dust opacity, okay, as well as water ice cloud opacity. Then our newer mission from 2006 through the present, still operating, is Mars Climate Sounder. Here we have a lot, because this was designed for atmospheric measurements, this is giving us a lot more vertical pieces of information. You can see independent information about 20 levels in the atmosphere. And we do that by looking through the limb. Okay, so this first is looking straight down at Mars. The second is looking at an angle passing through the atmosphere like this. Okay, so you see a lot more vertical information, but if there's thick dust clouds, you cannot see through them as well. So there's pros and cons to each type of measuring system that we can use for Mars. Okay. So the next part beyond the observations is we need a modeling system. Okay, so this is based on the GFDL Mars Global Climate Model developed by my colleague John Wilson, who's now at NASA. And this model actually shares a lot of things in common with the latest global forecast system model, which is what a lot of weather forecasts for the Earth are based upon. So kind of a similar dynamics, laws of physics. So in these, if you've ever taken a fluid dynamics class, you might think about conservation of mass and momentum and energy, right? These models essentially have those processes encapsulated, as well as representing things that are happening at the small scale, like what's going on inside a cloud, right? What's the radiative transfer going on inside the atmosphere? What's happening at smaller scales, such as turbulence, that we can't represent on the grid point. Okay? So very similar to the Earth, except there's some things that are unique for Mars, right? Mars has its unique atmospheric constituents, mostly CO2, much thinner atmosphere. So you can imagine the radiative transfer modules are going to have to adapt to that. We definitely want to include the impact of dust for Mars, where we might, in many cases, neglect that for Earth. Okay? And we want to maybe even think about how that CO2 atmosphere and how that cycle is going to change over the year. So there's some unique aspects to this model. Okay? The model resolution or grid spacing is about 300 kilometers. So we're using this model to look at large global scale to synoptic scale weather systems, thousands of kilometers across. Right? If we wanted to look at the details of something going on in a crater where we have a lander, then you might want to use a higher resolution model. Then we have about 28 vertical levels in the atmosphere, going up to about 100 kilometers in height. Okay. For those that study the Martian upper atmosphere up here, you'd probably want to go further up if you want to compare to, for example, MAVEN observations. Okay, so what does Mars look like if we look at some examples of the simulation? So taking a look here, we can see this is latitude and longitude. So these are just maps. The lines here are topography. So this is the Hellas Basin. This is the Tharsis Plateau. And colors are temperature. Okay, so the warmest temperatures are right beneath the subsolar point, cooler temperatures in the polar night as well as the nighttime. And as that sun moves across the planet, so do the warmer temperatures follow. Okay, that makes sense, right? But on Earth, we don't have this extreme difference of approximately 100 degrees Celsius between day and night in some instances. Right? Why is that? Well, Mars has a really thin atmosphere, and it's going to respond very much strongly to the changes in having solar radiation in the daytime and then kind of cooling at nighttime. Okay? Desert environments on Earth are probably the closest analogy, except we're not in these really thin atmosphere like we have for Mars. Okay? So this is going to be pretty extreme and different than the Earth. Okay? So how does that extreme change in temperature impact things? Well, this is kind of a diagram of temperature going through the local time of day. Just like Earth, temperature typically drops until right around dawn. Get your first rays of sun over the horizon, start to warm the ground and the air above it, right? Rapid warming until maybe early afternoon, start to cool off in the evening, okay? No surprises there. And what's different is because these changes in temperature are so extreme, they excite planetary scale waves, right? And those planetary scale waves actually give you big pressure oscillations. So if you had a Mars barometer, you'd see the pressure go up and down every day. And what's interesting about it is there's not just a single oscillation, but there's diurnal tides, right? 2 peaks in a day in pressure field. Right? And the tides complicate things. So if you want to look at kind of your traditional Martian weather maps, you need to maybe filter out some of these other tide modes to see about the changing weather. Okay? The tides do respond to the weather. During dust storms, the tides are much stronger, at least some of the tide modes. Okay? So there is some interaction between those two. Okay? So these tide modes are propagating across the planet in temperature and pressure. So that's an important feature of Mars. Right? And sometimes crater locations, like where our Curiosity rover amplifies those signs, and they're even stronger. So what does it look like at the seasonal level? Okay, so these are observations from a few different rover observations. And this is LS, so going across the course of a year. And what you're seeing is the atmospheric pressure changes from 900 pascals to 720 pascals. Right? What that really is saying is about a quarter of the Mars atmosphere freezes to the ground every year. Right? We do not have that analogy on the Earth. Okay? So why is that? That's again from kind of it's cold enough that CO2 can either directly go from vapor to solid and have the CO2 snow. Okay, so we need to, when we're looking at surface pressure signal, keep that in mind that the dominant signal is going to be, first of all, the seasonal cycle, and then second, the thermal tides. If you take out those two, you get the weather, which is the thing I'm interested in studying most. Okay, you can also get a sense of the variability, right? Even though we have the seasonal cycle, if we zoom in, we actually do have day-to-day variability of weather. And especially you'd see this jump out if I showed the dust storm years. Okay. So on the seasonal cycle, we could also think some commonalities with Earth. Right? For Earth, we might have heard of a jet stream. Right? Just let's say about 2 weeks ago, we had extreme temperatures where Mount Washington, a wind chill of minus 108 degrees Fahrenheit. Polar vortex this was displaced from the pole, allowing colder air to come southward. Mars also has a polar vortex. Dust storms can displace that off the pole. Okay? We have strong jet stream of winds moving really fast in Mars. You're about 100 meters per second, high up in the atmosphere. Okay? We see that in common with the Earth. These are westerly jets, okay, in the mid-latitudes. What's unique about Mars is in the winter seasons, we actually get the warmest day average temperatures close to the pole because we don't have the mitigating impacts of the oceans. So here we get air rising in the Hadley circulation extending across the planet. That's something we don't see on Earth. On Earth, we see something more like the Mars autumn, where we have a kind of a rising cell in the equator and then sinking motion about 30 north. Mars extends a little further. So this is a little more unique to Mars. Okay, so Martian polar vortex dynamics is another area of study. Right. So we had talked about observations. We talked about our model. How do we put those two things together? How many of you have probably heard of Bayes' theorem? Right? You start with prior knowledge of something. Right? Maybe you're saying, well, based on yesterday's weather forecast, it's going to be 30 degrees outside this morning. I might think about wearing my coat. But then just before you leave, you look at your home thermometer and it's actually 20 degrees. So then you adjust kind of your forecast based on those two things. And now you have a posterior, right? You know even more accurately what the temperature is. Okay. So here we're going to start with our prior. This is from a previous forecast of our model. We get new information coming in from our observations. And then we use our data assimilation system, in this case, the LETKF, to come up with our update or our analysis. Okay, so this analysis is using previous forecasts plus new observations to say, what is the weather like at this time in the Martian atmosphere? Now, we care not just what the weather's like, but we care how confident are we in that assessment. So for that, we want to run multiple copies of the model, right? Because we're not really sure which of them is most accurate. Okay, so we want to be able to characterize the uncertainty in that. Okay? So running then our next forecast into the future, we're going to run, let's say, 16 copies of the model. That gives us a sense of how certain we are in the temperatures and winds and pressure. And then we compare to the observations next hour that are coming in. And through that, we're trying to get a picture of what the Martian weather is like every hour across many years. Okay? This is similar to what we do for Earth reanalyses, looking at weather on Earth every few hours over many years. Okay? So in the end, we get our EMARS system. This is Ensemble Mars Atmosphere Reanalysis System. So combining these spacecraft observations that I talked about with the model, and in the end, we actually get more than 8 Martian years. That's going to be more than a decade on Earth of weather. So you could pick a date from sometime in the late 90s to close to the present, so maybe through many of your lifetime, and say, what was the weather like on Mars on that particular date, on that particular hour? And EMARS, in many cases, will be able to give you a map of that answer. Okay? So that's what we make this product. We can then explore some of the fundamental science questions that we want to explore about Mars using that product. Another part of this is technique development. These same techniques are used for understanding weather and climate on Earth. So if we can get more robust modeling, more robust data assimilation systems that are applicable in a wide variety of contexts, that's going to be helpful for better improving weather prediction on the Earth, and links into kind of the Earth side of my weather prediction work. Okay. So from here, we have hourly fields of temperature, wind, surface pressure, dust, water ice, any things that you might be interested in to study, things like dust storms. We know kind of the mean and its uncertainty or confidence. And we also have a control simulation where we did not use the observation information. So we could ask, well, how valuable was this observation information in constraining our understanding of Mars's weather? Okay. So this reanalysis is published and publicly available here at the Penn State Data Commons. And here's an example visualization of Martian weather, which I'll explain a little more in the future what we're seeing here. So this was done with a lot of different help from different collaborators as well as students here at Penn State. Okay, so now that we have a reanalysis, we might ask the question, well, how good is it? Right? You imagine if there's not that many observations on Mars, you might not know whether it's good or not. Well, we actually do have a number of independent observations on Mars that we can compare to. We could also compare to other systems that use completely different modeling systems, completely different data assimilation systems, and see how well we do. And finally, we can look at how we do compared to other different systems and weather phenomena. So this is an example of two completely different reanalysis systems. This is the MACDA system from collaborator Luca Montabone. Here's EMARS data assimilation system. We're comparing then to some independent observations. The MCS was not used here. And what we found is that the two reanalyses are more similar to each other than the two modeling systems by themselves. Okay, so that's really encouraging because that's saying that the observations are pushing us toward what we think the real atmosphere of Mars looks like, rather than just letting the models simulate whatever they want to do. Okay, so that's a preliminary vote of confidence in our work. Okay, so we've evaluated and studied a number of different science questions from zonal mean circulation, thermal tides, polar vortex, dust, transient eddies, dust storms, water cycle. But I'm going to focus mostly on these kind of traveling weather systems and dust storms for today's talk, dive into some more depth. Okay. So let's now start to ask about our science questions on Mars. Okay. What are we curious about? And the first one is going to be, what does a Martian weather map look like? Okay. So here's an example. Right. These, first of all, this is a northern hemisphere snapshot of Mars. So if this was Earth, this would be kind of looking from North America to Europe to Asia, okay, where we might have traveling weather systems move across in the mid-latitudes. On Mars here, what we have here in color, these are temperature anomalies. So I filtered out the seasonal cycle. I think filtered out the thermal tides. Okay. Then here we have winds in the arrows. And then these lines in black and gray are isobars, or lines of constant pressure. Okay. So just like you'd see on a weather channel map, you might have, for example, a low pressure right here. And you might have a cold front that's going between this cold blue anomaly and this warm area right here. Okay. And then you do have a warm front extending elsewhere. So that same paradigm of cold fronts, warm fronts, highs and lows that you would learn for Earth meteorology actually holds in the Martian mid-latitudes as well. And these systems typically move west to east. This is an example of a wave 2 pattern. You can see 2 cold and 2 warm anomalies here. On Earth, we have a bigger planet. We have a similar Rossby radius of deformation, meaning the weather systems are similar in size. But what that means is on Earth, we usually have 3 to 7 weather systems rather than just 1 to 3 on Mars. So we can look at these weather maps across the entire planet. Here's another example. Here's maybe what's unique on Mars is sometimes these weather systems extend all the way from the polar regions all the way to near the equator. Okay. Now these winds along here, right? Imagine if you have wind passing over a dusty environment like you saw with Curiosity. What do you think is going to happen to that dust? Right? That dust can get lifted by the winds, and that can be the start of a dust storm. Okay. So on Mars, we have common local dust storms happening almost all the time, right? Along this cold front, you have some winds, you have a little bit amount of dust lifted, right? But then the next bigger size storms, we want to think what's going to be happening uniquely. Okay, so we'll get to those next. But in order to understand that, we want to understand these traveling weather systems that we see. So to understand these, we can imagine how comparing these across different modeling systems. Okay, so this is a type of diagram called a Hofmöller diagram. If you haven't seen one before, this is longitude here, and this is time. Okay, so you can imagine if you're following a Martian weather system, you're starting out here, and tracking it as it moves from west to east across the planet. It gets a little stronger here, a little weaker here, and then shows up on the other side of the planet. Okay, so we want to see if EMARS says there's a weather system here. Okay, is there also a weather system in MACDA, a completely different reanalysis? Right, and how does that compare to the model without being constrained by the data? Okay, you can see the model behaves quite differently. It's a lot more regular. We're here with the observations. We should, for the most part, be tracking the meteorology, but you do see some differences here in the detail, right? So that kind of gives us some confidence down that should we trust every single one of these storms in their track? Probably not, but overall, we did some kind of quantitative assessment and we're somewhat encouraged by the degree of comparison between the two. So we also looked at some climatologies of these eddies. Again, these are kind of in the lower atmosphere, the lowest 10 kilometers or so. And these are the ones that are lifting the dust to start some of the dust storms. Okay, so looking at what these might look like at a seasonal time scale. So where do these storms happen? Well, thinking about the Earth, right? A lot of weather systems are happening kind of in the mid-latitudes where we have strong temperature gradients. Where is there a strong temperature gradient on Mars? Well, think about that polar ice cap. The sublimation point of CO2 is about 150 Kelvin. So over the polar ice cap, you're very cold. If you have bare rock just south of that, let's say in the northern hemisphere polar ice cap, that's a strong temperature gradient. You're setting up what we call in meteorology baroclinic instability. That's going to give rise to weather systems. So right along this ice cap edge here, this is the ice cap edge, you actually see that's the area for the strongest eddies. Autumn, winter, spring, and in the summer, there's no temperature gradient anymore. You don't really have many eddies in that hemisphere. Same thing here in the southern hemisphere. Okay, autumn, fall, there's this kind of pause in the winter, not fully understood, but there's some analogy in the North Pacific storm tracks on the Earth for that. We could ask what wave numbers are present. That's how many weather systems if we looked a great circle route around the globe. And typically 1, 2, or 3. And what's interesting for Mars is there's somewhat of a seasonality to this. On Earth, that's a little less pronounced. I think there's a little bit more regularity to the Mars systems, but there's still chaos and would still be trouble forecasting these, but a little more regularity. And if we break these down by season here, these are different Mars years. Okay, we can see that, for example, at this time of year, it looks like maybe 4 to 5 out of 6 years, we're getting a wave 3 pattern. What's interesting about a wave 3 pattern is this tends to actually get a dust storm starting in the mid-latitudes and then extending down toward the equator, and then sometimes even the southern hemisphere. So now we're connecting these weather systems to that continent-scale dust storm that can happen. Okay, the next thing we want to look at is what do those storms look like, and then how do we ever get global dust storms? So here's an example. If we took our reanalysis output and overlapped it on satellite imagery. So this is looking in the visible. You can see lots of different colors here. Part of this is the surface features of Mars, like the craters, but you have to look more at the texture. So you can see kind of the fluffy type of texture right in here. This is actually actively lifted dust. And right in here is the Martian cold front. And that's kind of that potential correspondence between where we have winds lifting and transporting the dust and lifting it at the ground. So part of what we want to do is assess how accurately can we actually assess where these traveling weather systems are, linking it to the imagery for dust. Okay? So we have dust being lifted, right? You have these narrow frontal systems like we have for the Earth. Okay? Here's another example looking at the pole. Okay? This is the North Pole. Right here at point A, you can see this linear feature. This is a frontal dust storm. And just like you'd see a cold front for the Earth. On the Earth, right, you'd see clouds, but they'd be water clouds instead of dust clouds, right? But sometimes if a cold front passes over a dusty place, let's say the desert Southwest or portions of Africa, the Middle East, you would see a pattern like this. Okay. So what does a regional dust storm look like? So here's one of these wave 3 patterns. It starts in the northern hemisphere, migrates its way south. Okay, this is dust with the redder colors representing more dust. And this regional storm reaches down to the southern hemisphere, lasts about a week, and then dissipates. These happen most Martian years. Okay? But what we're going to see is that the 2018 dust storm started this way, but then did not just simmer out in about a week. It actually grew to a global dust storm. We want to study why did that happen. Okay, so let's take a look first at climatology of dust storms. We're going to study them. We need to know how often they happen. Right? How often do we get a global dust storm? So this is 7 different Mars years. This is dust opacity with the redder and then pinker colors representing more dust. This is latitude, this is time or season. Okay, so this Mars year 24 might be a typical season. You have the dusty season, LS 240, basically northern hemisphere fall into winter. Okay. You get regional dust storms in here, that would be like these redder colors. Okay. But no global dust storm. Only 2 out of these 7 years you have a global dust storm. This is an example of how long that dust storm lasts. This is saturating that color bar with opacities of greater than 2, lasting for months. So why did we get storms in Mars year 25, Mars year 28, Mars year 34? When will the next one be? Okay, that's what we want to try to find out. Okay, so this is an example. Here's the Opportunity rover. Here's the beginning of the dust storm. You can see it starting right over Opportunity, moving south, going to the southern hemisphere, expanding, dust expanding around the planet. Curiosity, further away, nuclear powered, not many issues. Opportunity gets darker and darker and darker, and then the rover dies. Okay, so here, it was unfortunate in the position of the rover. What we're going to study is how did this dust storm then get dust to circle the planet, right kind of in here. See how the dust expands across Mars. What wind pattern led to that? Okay, so to do that, we're going to use our Mars traveling weather system analysis. This is from our previous work from the Penn State News here. And this is relating to the work of my former grad student, who's now off at a postdoc, Hart Gillespie. And he was looking at the role of various wind patterns in transporting the dust. Okay, so first, the Hadley circulation bringing the dust toward the equator. This is the path of the dust storm and the particles heading from the mid-latitudes toward the equator. And then here, the Hadley circulation has rising motion. We also get rising motion because we have dust in the air. It's being heated by the sun. That's going to make it more buoyant. It's going to rise in the air. Okay? And that's actually going to have a day-night cycle, which you'll see. So you have the dust moving up and down, but eventually it gets entrained in the Hadley circulation and heads back aloft to the mid-latitudes. And at this point, it gets picked up into the zonal jet stream and then begins to be transported around Mars. And that's how we see that dust cloud begin to spread at the early stages of the storm. Okay, so how can we see this a little more quantitatively? This is EMARS. This is our reanalysis product. This is the jets. So we can get a sense of how strong are those westerly winds. These are the winds in the meridional north-south direction. So that's telling us how we take dust from the mid-latitudes to the equator and then back again. These are vertical winds, right? So up or down motions. So what the dust is doing between day and night, you can see these things flipping around quite a bit. Take a look at this panel specifically right here, and you'll see this dust actually going from night. It's going to raise in the day and actually spread out from the equator, right? Like this. So you have that day-night cycle, but within that, you gradually get the dust spreading out enough that it can get caught in here in that westerly jet and transported around Mars. Okay. So we can actually trace individual dust particles. Okay, so just like trajectory analysis, we put a particle, we imagine it starts out at one area, we can track it with the winds blowing it and see where we'll end up at a later time period. So we put up particles of dust at the place where the storm started, we track them, and they do head in the direction that we intended to. We see them spreading across Mars here. There's some sensitivity to exactly where you put the dust and how high in the atmosphere you put the dust. That's something we want future models to do a better job of. That's a challenge to be able to do that part. So we also tried to ask questions about, is the dust being transported by the winds, or is the dust storm itself actually moving? And we think there's a little bit of elements of both. Sometimes in the biggest dust storms, it's not that you just have a storm at one area, but that the storm then kicks off dust lifting in a different part of the planet, right? And that's what we did eventually see in this storm. So that's something we explored to try to get a sense that, yes, both of those are probably important. So how do we get dust going high in the atmosphere? These are things that the global model, our group, doesn't represent, but those that are doing mesoscale or really fine scale modeling have a study. So Amerik Spiga and Stott Rafkin are scientists looking at radiative dynamic feedbacks. So imagine here's a dust plume. You have it initially lifted. You have solar radiation coming down, warming that plume. Just like a hot air balloon, it's going to rise. Okay? And you can imagine, they're imagining a hypothetical dust cloud that kind of looks like our cumulonimbus for the Earth. Right? Because of buoyancy, not here because of latent heat release, but because of radiative heating from the sun is allowing that to rise to high altitudes. Because our model doesn't have that, that then limits how accurate you can capture kind of this dust motion. So future Mars models, even at the global scale, might need to have processes like this, even if they're happening at the really small scale. That's an area of active research in the community. Okay. So a question you might have, we're thinking about dust storms. Will we ever be able to predict them in the future? Okay. How well can we predict Martian weather? Okay. So while we haven't done this in real time, you can look retrospectively and see how well we can forecast the weather. So we, for example, start out from our reanalysis. We take away the observations and we just try to launch a model simulation going forward into the future. In other words, a retrospective forecast. Okay, so it stays better than the model running without observations for about 5 days or so. Okay, so that's maybe a first view of the predictability of Martian weather. Now, on one hand, Mars weather is easier to predict than the Earth because of the little bit additional regularity of the the traveling weather systems. But on the other hand, Mars has a fast radiative time scale. So if you have the dust in the wrong place, your forecast goes bad fairly quickly, let's say in the time span of a day or two. Okay? So I think dust storms will be especially challenging, even if we start to constrain the weather systems, knowing which of them will eventually develop in the global dust storm, that might be very sensitive to initial conditions and perhaps more challenging to represent. Okay? So where are we going into future observations? So in addition to the ones I've shown so far, this is from the Emirates Mars mission EMARS. And instead of just a single spacecraft track, this has a different orbit that's more elliptical. So it's looking at Mars from a little further away, and it actually almost gets a full view, like a geostationary satellite from Mars, except it's not parked over the same area. Okay? But you're seeing a broad swath of Mars. And that might be the next way to better constrain kind of Mars weather systems. Instead of just sampling a line through them, we're actually able to get a bigger view, at least when that spacecraft's overhead. Okay, so combining perhaps these data with the existing kind of polar orbiting satellites is something I see the field going in the near term. Longer term, we might want to think is, can we have aerostationary satellites? Some colleagues have thought about that idea. We have a few satellites parked over certain areas of Mars, getting a continuous view so that we don't have to wait for the spacecraft to pass over Mars again in another 12 to 24 hours in the future. Okay, so there's an active community thinking about these future ideas. Right? So there are other Mars meteorologists out there, even others looking at specifically prediction and data assimilation. Here's an example from a workshop in Japan that we are looking at Mars as well as Venus. They're actually a Japanese group that does Venus modeling and data assimilation. Here's kind of a Mars first data assimilation workshop for Mars in France in 2018. And we most recently had kind of the Mars community meeting this past summer in Paris, and there's about, I would say, 200 Martian meteorologists around the globe. So a much smaller field than Mars geologists, but it actually is a relatively large field, maybe compared to first impressions. Right? So good international collaborations. There's European missions, missions from the United Arab Emirates, India, China, other countries that are all kind of looking at the Martian atmosphere. Okay? So we hope to continue to learn more about the Martian atmosphere and discover its mysteries. So the last slide here that I'll show is, what is it like on Mars recently? So this is February 9th, 2023. There's probably maybe an updated one today. Here's the temperature, high is 0, low of minus 116. Okay, so the daytime, not so bad. Actually, on the ground of Mars, it might be 30 degrees. There's actually a huge temperature gradient from kind of the warm rocks that are getting directly to the solar insolation compared to higher up. It can actually get to maybe 60, 70 degrees Fahrenheit on the rock, maybe 30, 40 degrees Fahrenheit in the atmosphere at the warmest. But you can see at nighttime, you've got to be ready. This is worse than the wind chill at Mount Washington at its record. Okay? And that's just a typical day on Mars.